Alright, Chapter 9, Strength of Materials. Masad Ali, Alia, Professional Development, PhD, Professional Engineer. Introduction. Mechanics of material. The branch mechanics relates to the external loads applied with the body, with the equilibrium and internal force, with the subsequent deformation of the body, and the shape of the concept of the stress and the strain of the relationships are introduced. Deformation axial load members are also presented with the torsion of the bending of the structural members are analyzed. Structural under of the combined loading as well as the design of the columns is discussed. Normal stress, shear stress, normal strain, shear strain factor, safety relationship, stress strain, plastic behavior, thermal strain, posing and ratio to deformation axial load members, torsion bending, transverse shear stress, combined loading, principal maximum shear stress, thin wall pressure vessels, columns, deflection of beams, failure theory, summary. 1. Not normal stress of the shape of the bar with the concept of the cross section with a prismatic under the action of the constant force that is applied with the centroid of the bar. The stress of the defined is load P, defined by the area of the load per unit area. A is called the normal stress denoted by O as in and is positive. If the bar tension stress is called tensile strength, if the bar compressed stress is called compression stress, and that is negative. Stress units of the pounds per square inch or pounds an inch squared or psi in the English system, newtons per square meter or pascals in metric meter. So normal stress is the equivalent of the stress defined in load over the area. Tensile strength is positive, compressive strength is negative. Tensile figure 9.2 shear stress. Two plates both with the glue to each other the stress of the parallel area to contact area S. Or shear stress is called the average shear stress is noted as the average shear stress is equal to the shear load over the shear area. And for both the connection area shear stress, shear stress is the cross-sectional area of the bolt. Figure 9.3 show the bolt and velocity. 9.3 normal strain. Consider again the prismatic bar under the action of the tensile load with the initial length of the bar inerrant. The initial length of the bar is L after the load is applied with the bar elongates along the tensile. The stress elongates by stress. Average normal strain is defined with a ratio change with the length of the initial length denoted as energy average. If the bar tension is strain, the tensile strain is positive. If the bar is compression, the strain is called compressive strain. Is negative. Note the strain is dimensionless. So the average the average length ratio of the normal strain is equal to the stress over the length, which is either in tensile strain or compressive strain. 9.4 shear strain. Consider the stress elements under the action of the shear stress shown with the drawing below. Shear stress on each side of the face must be in the same order of the stress element remaining in equilibrium. Shear strain is denoted as Y. It is defined change the angle between two sides of the stress elements of the 90-degree initial angle. Shear strain is measured the distortion of the element under action. Shear stress. Shear strain is dimensionless and unit must be in radians. N5. Factor of safety. Factor of safety defined the ratio of the load stress with as cause of failure to applied load stress with applied load usually referred to as the allowed load. Failure load can also be taken as a yield of their ultimate load. Factor of safety is equal to the full load over applied. Factor of safety is equal to the stress of full and stress of all. Factor safety of the average full load over the all load. 9.6 relationship to stress and strain. Relationship with the elasticity electric strain is based on the law known as Hooke's law, or the stress is equal to the energy of the energy. So you have elastic bones, electric stress and strain. The energy is a material property known with a modulus elasticity. Young's module with the energy of the structural seal is 30 by 10 to 6 psi or 200 grams of pascal. The relationship between stress and strain of the represented graphically the energy slope of the shaded line is linear of zone. Although Hooke's law applied with a member of the pure shear and relates to shear stress to shear strain. and where G is a material property known as the modulus rigidity, and the slope of the line is the linear zone of the shear stress or shear strain plot. 9.7 Plastic behavior. In this chapter, we only consider loadings will cause the material that have elasticity. However, the Hooke's law is satisfied with the material load with elastic limit of load. At the limit removed, the material will return to the initial state with no radius residual strains. Some materials, such as mild steel, with the design with the yield of the load, therefore permanently deform. The stress various versus strain diagram for such material can be modeled in elastic and perfectly plastic electroplastic. One should note that all subsequent equations due to the axial loading, twisting, and bending of the member valid only with a linear and elastic zone. 9.8 Thermal strain of the bar is constrained with the temporary change of the bar will deform. The strain due to the change of the temporary is called the thermal strain, denoted as the energy strain as if the angle of the strain. 9.9 Poisson's ratio. Consider the bar under the actual. Here is a angle coefficient thermal expansion of the 1 over the degrees Fahrenheit is defined in strain with due to 1 degree change in temperature. Note that the angle of E versus the material property modulus rigidity is a material property. For example, structural steel. Is 12 to the negative 10 times 12 to the 10 to the negative 6 over the 1 to the degrees Celsius. 9.9 Poisson's ratio. Consider the bar under the action of the load, direction of the load axial, perpendicular axial, the direction of the lateral direction. The load is applied with the bar will elongate the axial direction, same time with the contract with the lateral direction. Poisson ratio denoted V as defined as the velocity of the defined the negative ratio lateral strain axial strain. The negative in this equation required to give the positive value of the velocity. Note the velocity of the material of the property. For example, the velocity of 3/10 of the structural steel. Also, Poisson's ratio V cannot be larger than a half. Three properties of the E, G, and V are energy and what's that G? Material properties, rigidus, and velocity related to either. See you later, Paul. Modular rigidity is equal to energy times over 2 plus 1 to the velocity. 9.10 Deformation axial load members. Axial load members, see figure 10, 9.10. Axial deformation can be determined by using the following equation. Strain equal energy and elasticity PA. 9.11 Torsion. If the straight bar constant circle cross section is a shaft of fixed one end of the speed width of the torque of the other end of the member is said to be the pure torsion. When the shaft of the twisted shear stress developed throughout the shaft, the result of the applied torque of the stress shears varies with the functional radial distance R. Maximum at the outer surface of the R is maximum R is equal to C. So you have torsion mass with the torsion R over J. J is the point of a moment of the narrow, and torsion max at torsion center equal over J. Note that the shear strength changing linear with the function radial position R. Here J is the polar momentum of the narrow with a circular cross-section shaft. J is the polar momentum of the air distance, pi times the distance to the fourth over 32s, or J is equal to pi the center's 4 to the fourth times 2 divided by 2 has units of inches and quadratic 4 meter quadratic twisting in which all shaft is deformed to distortion angle twist. Shaft length of the angle action of the torque is given with the equation as in the angle of the twist is equal to the action of the torque of the linear moment over times the model of rigidity times J, which was the moment of the inert. G is the shear modulus material property, with the dimensionless should be expressed in radians. Note that the hollow shaft of the polar moment inert J is given by and they give the equation where D is 0 and 0, 0 outside diameter radius respectively D1 and C1 are inside the D inside the diameter inside the center out inside is radius respectively. Alright, note that the non-circular section of shear stress distribution over the cross section is nonlinear as a result of the equation of the stretch torsion max of the torsion of the center over momentum and inherit. Alright, 912 bending. Beam that define long prismatic structure of the design to support loads various points along with a membrane. In most cases, the loads are applied with a perpendicular to the axis of the beam, cause only shear and bending of the beam. Internal forces and momentum is considered simply supportive of the beam, shown in figure 918. If the beam is caught by the current certain section is observed, the left or the right section to be in equilibrium, a shear load V. Bending momentum M must be presented in a section shear load over the bending of the moment and called the internal force. Note that figure 919 directions of the V and M are left of the right section of the beam and they indicate with a single of the conventions of positive shear and positive moment. Figure 919. To determine the initial forces moment to do with the following, determine the reaction support without the section for the internal force are to be calculated. Draw the free body diagram. Use the equilibrium equation to determine the internal force of momentum. To find the shear load, use the logarithm of force y is equal to 0. To find the M bending moment, use the logarithm of m and 0. Note the results seen regardless of section right left. Alright, shear bending moment diagrams. Since determination of maximum shear bending moment, it is important to design it more convenient to plot shear of the bending moment along with the beams to cut many of the sections, calculate these values. Graphs obtained and colored with the shear diagram and bending momentum diagram respectively. Drawing a shear and bending moment, the following relations for the distance dv over dx equals the negative angle, or derivative v1 over v2 v1 distance derivative over the negative x2 over x1 derivative angle times distance times x, where W is distributed load acting on the beam. Net shear force or area is under distributed by the x and 1. Net bending moment equals area under shear load from x1 and x2. And then we'll continue to go to stress due to bending. Consider a prismatic beam to be bent under the action applied load as shown. The bending stress, also known as flexural stress, is determined by using bending flexural stress is equal to bending moment at a given point over times y, the distance of the centroid and neutral axis of the point where the stress is to be calculated over area, momentum, and inherit respectively the axis bending through the centroid. The maximum bending stress is determined by using maximum bending stress over the bending of the moment at a given point of the centroid and inherit m over inherit moment over the centroid, where C is the perpendicular distance of the neutral axis to point farthest away from the neutral axis top-bottom fiber. Note that the stress distribution in cross-section linear stress is 0, centered in neutral axis. Alright, 913, transverse shear stress. Stress is developed in structural result of shear force. V is called transverse shear stress, is denoted T. Transverse shear stress is equal to the result of the shear force times the first momentum direction respective to the neutral axis over an area momentum and an area with respect to the neutral axis times the thickness of the beam at the position y, which shear stress is calculated. Note that the shear stress is 0 at the top of the bottom fiber is free surface maximum at which neutral axis of the transverse shear stress does not change linear but rather parabolically second order, shown figure 928. Solid rectangular cross section shear transverse 3v over results of the shear force over the 2a, which is 2 times the area of the cross-sectional area of the solid circular cross-sections. Tangential transverse shear stress is equal to 4 times shear stress at a given point times 3 times the area. 914, combined loading across interior structural members subject to some of the combination axial bending and torsional loads. To determine the maximum stress normal with the shear that first located at the point of the stress is most severe with the cantilever beam of the point is located with a fixed support. Once the stress is due with the differential loads calculated that can be represented a very small element, the stress element with the maximum normal and shear stress can be determined. The maximum normal stress are called principal stresses in planes over which these stresses occur and are called principal planes. Alright, 915, principal and maximum shear stress. To determine the principal stress and maximum shear stress, their planes. Use the following equations. Where principal angle and the maximum normal stress will occur, the similar angle shear strength angle is where the maximum stress will act. Alright, 916 thin wall pressure vessels. Cylindrical pressure vessels are used in the industry of the boiler and storage tanks. Thinner wall refers to the tank which ratio of the inner radius thickness is equal to radius 10 times the radius initial time the rate time divided by the time tension greater than or equal to 10. Cylindrical vessel, cylindrical inner radius and thickness that is under pressure P. Cylindrical circumferential hoop, longitudinal stress are developed in vessels. Cylindrical vessel, thin wall cylindrical vessel subject include inside pressure. Figure 934, stress is location given in an equation. Longitudinal pressure is equal to pressure 1, E pressure 2, or pressure of the radius. Inner radius over 2 times the thickness. 917. The columns that define long slender members of the longitudinal axial compression design column. The following rules must be followed. Normal stress due to the applied load should not exceed the allowable stress. Axial deformation should not exceed the allowable deformation. Load applied must be less than critical load causes buckling. If the column pin both ends smallest critical P is given them the equation. Note that inerrant moment, smallest moment of the inerrant is about any axis. Equation N30 knows the Euler's formula for other end of the equation can be used of longitudinal moment, energy, and effective length to the shown in the figure 936-4 conditions. Effective length distance between two consecutive inflection points of the elastic curve. 19. Deflection of beams. There are several methods which can be determined with the deflection of beams and transverse load. Some of the analytical methods include integrating superposition, momentum, and energy methods. However, we'll only discuss the first two methods briefly. Integration method, small deflection differential equation, elastic curve is given by elastic curve of the distance to the y over distance over the x squared equal to m, or elastic energy and equal to y equals to m. Y is the vertical displacement of the elastic curve. Deflection m is the bending moment of the general varies with the function position x. Once bending moment is determined, the differential equation can be solved with the integrating twice using proper boundary matching conditions. Constant integration can be determined in figure 937. Figure 919, failure theories. There are four theories that can usually predict failure to material under combined load if the material is designated. The ductile maximum shear strength theory, maximum distortion energy theory, even to predict the failure. Only other hand with a material brittle with a maximal normal stress theory and Muller's failure criterion used to determine the material will fail. We will briefly discuss two theories of the ductile material with the maximal normal stress theory of the brittle material with the equation with the presented valid two-dimensional plane with the stress of the fields. Maximum shear stress theory of the ductile material failure specified with the initiation of the yielding both methods. One's principal stress 1 and 2 calculated with the given plane of the stress elements following with applied principal stress 1 and 2 have same signs then for failures not to happen. Principal stress 1 absolute and 0 is greater than stress less than stress y, and absolute stress principal stress 2 is absolute value is less than y. Principal stress 1 and 2 have opposite signs, and the failure is not to happen. Principal stress 1 minus principal stress 2 is less than principal y, where principal stress y is yield stress and material property. Maximum distortion energy von Mises, also known as von Mises final theory, failure theory is valid for the ductile materials for material not to fail. Following equation has been satisfied as principal material stress 1 squared minus principal material times material 2 plus material principal 2 squared equals is less than principal stress at y squared. 3. Maximum normal stress theory of the brittle material fracture happens on not much wielding. The theory of the fracture came to the normal stress for the yield of the ultimate stress. Once the principal stress is calculated with a given point stress elements file with applies. Principal stress 1 is less than principal stress, ultimate stress, and principal stress 2 is absolute is less than ultimate stress. Alright, 92070. In this chapter, the concept of the stress and strain of the relation between the average number of stress with the defined ratio of the potential load with the cross-section area with the average stress, shear stress defined with the ratio shear stress, shear load, shear area, deformation due to the axial load as well as change of the temperature. Also presumed in the chapter equations calculated the last static stress due to the bending and the twisting discusses as well. Critical buckling load calculation. Remember the compression differential support conditions presented the deflection beams using different methods. Combined loading stress transformation failure theories. Also to discuss examples as shown. Alright, Chapter 10, Material Properties.